Welcome, everyone! Today we are exploring a highly specialized explainer on exponential calculations. We've designed this entire session directly from the Cambridge 0580 mathematics syllabus materials to get you completely 100% exam ready. Now, I know exponential equations can look super intimidating when you first see them on a past paper, but here's the secret. Whether you're dealing with compound interest rapidly building up in a bank account or a radioactive element that's slowly fading away over time, the mathematical mechanics under the hood are exactly the same. Literally, the identical engine runs both of those scenarios. In this explainer, we're going to break down those core mechanics step by step, so that the next time you face one of these high-mark questions, you can tackle it with total explosive confidence and maximize your score. Okay, let's take a quick look at our roadmap for today's strategy session. First, we'll unpack the constant multiplier concept. Then we move into calculating exponential growth, followed by real-world growth scenarios. After that, we'll flip it around and look at calculating exponential decay, see depreciation in action, and finally wrap it all up with a key points summary. Let's see exactly how a single variable dictates whether a value absolutely skyrockets or just slowly fades away. Section 1. The constant multiplier concept. We begin our entire journey today by anchoring everything around one absolutely core mathematical engine. So the crucial point I want you to grasp right out of the gate is that whether we're looking at compound interest increasing your savings or dropping populations of wildlife in a biology problem, this constant multiplier is the secret key. Seriously, if you understand this one concept, everything else just falls perfectly into place. It's defined as the fixed numerical factor that you use to repeatedly multiply a quantity over a specified period of time. It's the absolute engine of continuous change. Think about it like this. Instead of just adding or subtracting a flat amount each year, like simply adding $10 to an account over and over, which is linear, you are scaling the value by this exact multiplier repeatedly. It compounds. It builds on itself. This is what separates top-tier exam answers from the rest, understanding that we are dealing with continuous, multiplicative change, not just simple addition. Section 2. Calculating exponential growth. Let's take this theory and actually see how this multiplier builds when we apply it to something that is actively growing. Now, what's really interesting about this slide is how we can visually track a $200 investment growing at a rate of 5% per year. Before we continue into the really heavy lifting, subscribe to our YouTube channel, Ace the Exams at acetheexams_IGCSE to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now. Okay, look closely at this table. Notice that we don't just add $10 every single time. Instead, we are multiplying by our constant multiplier 1.05. Where does that come from? Well, you keep your original 100% and you add 5% growth, giving you 105%. As a decibel, that is 1.05. In year 1, 200 times 1.05 gives us $210. Simple enough, right? But look at year 2. We take that original 200 and multiply it by 1.05 twice, giving us $220.50. Notice that extra 50 cents? That's the compounding effect. You're earning interest on your interest. By year 3, we're multiplying by 1.05 3 times to reach $231.53. The math is repetitive and it constantly scales based on the previous year's new total. Now, writing out 1.05 over and over again is totally fine for 3 years. But what if the exam question says you leave the money in the bank for 20 years? You definitely don't want to be typing that out manually during a timed exam. And this brilliantly illustrates why we use the powers key on a scientific calculator. It is a massive, absolutely essential shortcut that saves us from doing endless manual multiplication. We simply take the repetitive multipliers and compress them into an exponent. So 200 times 1.05 times 1.05 times 1.05 simply becomes 200 times 1.05 to the power of 3. Mastering your calculator's functions is a huge part of your exam strategy. By extracting that pattern from the previous steps, we land squarely on this elegant algebraic formula that you can apply to literally any exponential growth scenario. The formula is A equals 200 times 1.05 to the power of n. Let's break that down so there's no confusion. Here, A is the final amount of the investment, the answer you're looking for. 200 is your principal, or starting value. 1.05 is your constant multiplier, which perfectly represents a 5% growth rate. And finally, n is the number of years, or whatever unit of time the question uses. Once you have this blueprint, you can plug any number of years into n and instantly see the future value. This formula is your best friend. Section 3. Real-world growth examples. Let's step away from the bank for a minute, because this mathematics isn't just for money. It actually governs the natural world around us, too. Look closely at this source example directly from the syllabus, where a population of bacteria doubles every single hour. If you start with 500 bacteria at noon, how do we find the amount later on? Well, because it specifically says doubles, your constant multiplier here is simply the number 2. So after 1 hour, it's 500 times 2. After 2 hours, it's 500 times 2 to the power of 2, which immediately jumps to 2,000. See how aggressively that scales? And if an exam asks you to find the population after an unknown number of hours, represented by n, the calculation is elegantly written as 500 times 2 to the power of n.
Section 4. Calculating exponential decay. Okay, now we are going to flip the script entirely and see what happens when things start to shrink instead of grow. Stop scrolling. Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. We've helped thousands of students improve by 2-3 grade boundaries. Join them right now by subscribing to at acetheexams_IGCSE and turn on all notifications so you never miss our weekly exam strategy sessions. All right, let's look at this comparison. The math works exactly the same way whether we go up or down, but the absolutely critical takeaway here is the pivot point, the number 1. If your constant multiplier is strictly greater than 1, like 1.05 or 2.0, you have exponential growth, and your n value gets bigger. But if the constant multiplier is less than 1, say 0.85 or 0.9, the result inevitably gets smaller and smaller with every single multiplication. This is what we call exponential decay. Multiplying by a fraction of a whole means you are losing a piece of it every time. Walking through this bat population example step by step is going to make this super clear. We start with a population of 140 bats, and the exam question tells us they are declining by 15% a year. The very first, absolutely crucial step is to find your multiplier. Do not, I repeat, do not just use 0.15. If you do that, you're calculating how many bats died, not how many are left. Instead, you take the full 100% and subtract the 15% decline. That leaves you with an 85% retention rate. You then convert that 85% into a decimal, which gives you your true constant multiplier of 0.85. To find out how many bats are left after 10 long years, you set up your equation, 140 times 0.85 to the power of 10. Punch that into your calculator, and you'll find the population has aggressively reduced to just 28 bats over a decade.
Section 5. Depreciation in action. Let's look at how this exact concept of decay applies to the physical assets we buy and own in the real world. And honestly, this brilliantly illustrates the real-world pain of buying a new car. In this syllabus example, a car is initially valued at $9,000, but it decreases in value by 12% every single year. So let's use our rule. 100% minus 12% leaves us with 88%. That means our constant multiplier for this calculation is 0.88. To find the car's value after 3 years, we calculate $9,000 times 0.88 to the power of 3. Your calculator will spit out $6,133.25. That is a massive drop in value, all driven by that multiplier being less than 1. I want you to pay very close attention to the terminology here. If you see the specific command word or term depreciation on your Cambridge exam paper, you immediately know you are dealing with exponential decay, and you must find a multiplier that is less than 1. It is simply the financial term for an asset losing its value over time at a consistent percentage rate. Don't let the vocabulary throw you off. It's just the bat problem, but with dollars instead of animals. Okay, it is interactive workshop time. Grab your calculators right now because it is time to put this strategy into practice. I want you to apply the decay formula to this specific scenario. A 50-gram radioactive element reduces its mass by 10% each year. What will its mass be after precisely 3 years? Take a second. Remember the golden rule, find your multiplier first before you do anything else. All right, did you get it? Let's check your work. If you took 100% and subtracted the 10% loss to get 90%, you correctly found your multiplier of 0.9. From there, if you took your starting mass of 50 grams and multiplied it by 0.9 to the power of 3, you perfectly executed the decay calculation and arrived at exactly 36.45 grams. If you got that right, you are well on your way to mastering these questions. Let's switch gears back to growth for this next speed exercise. Tony has a boat, and he says it's increasing in value by 6% a year. It's valued at $25,000 right now. Pinpoint the correct multiplier for a 6% increase and apply it over a span of 6 years. Oh, and here's the catch.
Pay incredibly close attention to the specific rounding instruction at the end of the question. The examiner wants the final answer to the nearest $100. This is exactly where students lose easy marks.
Let's break it down. Your constant multiplier for a 6% increase is 1.06, so the core calculation is 25,000 times 1.06 to the power of 6. If you put that in your calculator, the exact calculation yields $35,462.97. But properly rounding that figure to the nearest $100, as the examiner specifically requested in the prompt, brings us to $35,500. Nailing that rounding instruction is exactly what secures you full marks. Never ignore the final sentence of an exam question. Section 6. Key Point Summary. As we wrap up this explainer, let's condense everything we've covered today. Students who implement these mathematics strategies see an average improvement of 2 grade boundaries, but only if they practice consistently with our weekly videos. Let's look at the absolute golden rules you need to lock in. Here are the 2 unshakable pillars of exponential mathematics that you should screenshot for your revision right now. If it's growing, your constant multiplier is greater than 1. If it's decaying or depreciating, your constant multiplier is less than 1. The formula structure remains exactly identical. It is all about finding that correct multiplier. Here's your final reminder. Subscribe to our YouTube channel Ace the Exams at AceTheExams_IGCSE to excel in your Cambridge examinations. Subscribe right now to at AceTheExams_IGCSE and click that bell. Don't let another exam pass you by. I leave you with this thought to ponder today. Once you truly understand the constant multiplier, you literally start to see it everywhere. From the way viral videos explode across the internet, to how quickly a brand new phone loses its value the moment you open the box, to how your investments build wealth over decades, it is all governed by these exact same mathematical rules. Drop a comment below with your target grade for mathematics and the biggest challenge you're facing. Our team responds to every comment. Like and share this video with a study partner. Ace the Exams. Your Cambridge success starts here.